Welcome to Mathematics for Computing module that is for BSc Computing Systems for Ulster University. My name is Faisal Hashmi. Week 1 is about numbers. The learning outcomes are understanding the meanings of sets of numbers and calculate the sum of sequence of numbers represented using sigma notation and calculating the product of sequence of number using pi notation, simplifying expressions involving exponents, and calculate the logarithm of a number in a given base, converting a mixed number from base b to base 10, and converting an integer from base 10 to another base, convert an integer from base 10 to binary 2's complement, and converting an integer from binary 2's complement to base 10. Natural numbers are the numbers that we use to count, namely 1, 2, 3. And you may have heard such numbers described as whole numbers. The set of all natural numbers is denoted by n, and we have elements 1, 2, 3, and so on, 4, 5, 6, 7. It's obvious that it is a continuous pattern, and the numbers are going on and on and on. Numbers like 1, 2, 3, 4, 5, 6, they are called element, like 1 is element of natural number, 2 is element of natural number, and we can call because continuous pattern, we can call 100 is element of natural numbers. Integers, this is a set containing all the natural numbers, their negative counterparts, and 0 is represented by z, and the elements are -3, -2, -1. It includes 0 as well, 1, 2, 3, and so on. The set of all positive integers is denoted by z plus. It would be 1, 2, 3, 4, and so on. The set of all negative integers is denoted by -1, -2, -3, and we are using z minus for this one. Real numbers, any number which falls anywhere on the number line is a real number. The set of all real numbers is denoted by R, and the set of all positive real numbers is denoted by R plus, and set of all negative real numbers is denoted by R minus. And when we'll be looking at number line, we got 0, 1, 2, 3, and similarly -1, -2, -3. All the numbers that are between, let's say, -1 and -2, all those numbers, they are member of set of real numbers. For example, we can call it 2 is element of real numbers, and of course a half is element of real numbers, 0 is element of real numbers, square root of 2 is element of real numbers, but remember -1 is not element of real number. The set of rational numbers is denoted by a Q. That are the real numbers which can be expressed as a fraction, for example P over Q, such that P and Q, they are element of integers, and the denominator is not equal to 0. Examples are, we can say that half 1/2 is element of rational numbers. We can call a maybe 0.127 as a element of rational numbers. -7 is an element of rational numbers, but remember 2 square root is not an element of rational numbers. Similarly, when we'll be looking at irrational numbers, if we'll like subtract all the rational numbers from the real numbers, the remaining would be irrational numbers. Exercise, which of the sets in ZQR are the following numbers members of? First of all, we have -155, that is an element of rational numbers, integers, and real numbers. Second one is 234 divided by 78, that is equal to 3, and it would be a member of rational numbers, natural numbers, integers, and real numbers. Next one we got 0.9, and we can see that it's a recurring decimal recurring number, that 9 is coming repeating itself, coming again and again. So we know that 0.999 is almost equal to 1, and 1 is an element of natural numbers, integers, real numbers, and of course rational numbers. The next one is square root of 5, that is an element of real numbers. Remember, the square root of a non-square number is not rational. Sigma notation is a method used to write out a long sum in a concise way. We look at ways of using sigma notation and establish some useful rules. In order to master techniques explained here, it's vital that you undertake plenty of exercises so that they become second nature. Let's say we have one sequence of numbers starting with A1, A2, A3, A4, and so on. And we can use a sigma notation to sum up that sequence of numbers. We can write one sigma notation. This is known as sigma, and the sequence is starting from I is equal to 1, and last term it's a, let's say, an. The last term is an ai. Remember, this is the starting point of that sequence, and this one n is the last term in that sequence, and we can write it out like this: a1 plus a2 plus a3, so on till an. We can add that sequence. Exercise for sigma notation: write each of the following expressions as a sum and evaluate it. We got sigma I is equal to 1 till 4i. In that case, we will write 1, that's I is starting with this value, and then the second one would be its increment by 1, it would be 2 plus again increment 3, and then we will have 4. We can see that the last term is 4, so we need to stop it there. We will be adding 4, 3, 1 and 2. It would be equal to 10. In another question will have sigma notation, I starting from 1 till 3, I square. To start with, I is starting with 1, so we'll write 1 square, and with the increment of 1 it would be 2 square, and it would be 3 square. The last term is 3, so we need to stop it there. We'll evaluate it. 1 square is 1, 2 square is 4, and 3 square is 9. Once we'll add them, we're gonna get 14. In question number 3, sigma I is starting with 6 and the last term is 8, I over I plus 2. To start with, we know that the value of I is 6 over 6 plus 2. With the increment of 1, the next term would be 7 over 7 plus 2. And the last term, we know that it's 8. We'll write 8 over 8 plus 2. We can simplify that one. 6 over 6 plus 2 is 8, plus 7 over 7 plus 2 is 9, plus 8 over 8 plus 2 is 10. You can use a calculator to figure out whatever would be the answer for this sequence. Pi notation, pi is a letter in Greek alphabets, and it is used in mathematics to represent the product of a bunch of terms. It is used in the same way as a sigma symbol that we have described in last slides, except that the succeeding terms are multiplied instead of adding. Suppose we have sequence of numbers that is A1, A2, A3, and so on. If we have to denote them in by using pi notation, what it would be I is equal to 1 till, let's say, the last term is an, and we'll write a I. There's a way of writing them, and it would be a1 multiplied by a2 multiplied by a3 multiplied by a4 and so on, an minus 1 multiplied by an. We know that the last term is n, so n is the last term, so an would be the last term. We can take another example. We can write let's say I is starting from 1 till 4, and I, it would be equal to 1 multiplied by 2 multiplied by 3 multiplied by 4. At this point, we know that the value of I is 1, and here value of I is 2. Here we got I is equal to 3, and of course here we know that value of I is 4. Once we're gonna multiply all these terms, 4, 3, 12 times 2 is 24. Let's look at one more example. We got pi, that is I is starting with 4 and the last term is 7 I over I plus 1. So we need to start with we know that the first term is 4. So 4 over 4 plus 1 multiplied by 5 over 5 plus 1 multiplied by 6 over 6 plus 1 multiplied by 7 over 7 plus 1. Once we'll simplify them, we know that we're going to get 4 over 5 multiplied by 5 over 6 multiplied by 6 over 7 multiplied by 7 over 8. And once we're gonna simplify them, we're gonna get 1 over 2. Just a thing to remember, I is starting with 4. So we will be having first term as a 4. And the last term is 7, so we need to stop at 7. Base and exponent. Usually a power is represented with the base number and an exponent. For example, if we have a to the power n, it means a is multiplied by a multiplied by a multiplied by a and multiplied by so on by a. It means n copies of a in this product where n is element of natural number. Remember, when we are writing a to the power n, in this case a is the base and n is the exponent. Sometimes also called the index of power. Let's take another example. If we have 4 to the power 2, it means 4 multiplied by 4. If we have 2 to the power 3, we're going to write it 2 multiplied by 2 multiplied by 2. In terms of negative exponents, they are defined as we got b to the power minus n, it would be 1 over b to the power n. Or if we have 3 to the power minus 2, it would be written as 1 over 3 to the power 2, that is equal to 1 over 9. Remember, if we have minus 3, 3 to the power minus 2, it would be, it's gonna get, this minus gonna get converted to plus in the denominator. And one generic rule, that is a to the power 0 is always equal to 1 for all non-zero a. We can say that x to the power 0 would be equal to 1. Anything to the power 0 is always equal to 1. Laws of exponents. When expression with the same base are multiplied, the indices are added. For example, if we have a to the power m multiplied by a to the power n, it would be equal to a to the power m plus n. We can see that we have same bases here. When we have same bases, we can write one base and then the indices, the powers m plus n, they're gonna get added. And when we have expression with the same basis, they are divided. For example, if we have a to the power m divided by a to the power n, in that case the indices are subtracted. We can write one base a and m minus n. The powers of a, that is m and n, they will be subtracted. The third one is if we have a to the power m whole power n. In that case, this m and n, it would be multiplied and we'll get a to the power mn. Remember, if we have a to the power 1 over 2, it means square root of a. And if we have a to the power 1 over 3, we're going to write as a cube root of a. And similarly, 1 to the power a to the power 1 over n, it means nth root of a. Simplify each of the following, writing your answers using positive exponents only. We can simplify this question. We can write 6y to the power 2 because the power of y is -4. We can take in the denominator. It would be z to the power +4. Similarly, in this case, we have 6xy to the power -2. We can write 1 over 6xy to the power 2 or +2. This plus is just to show you that it was -2, and then we have taken that one into denominator. That has changed -2 to +2. We can simplify it a little bit using laws of exponents. We can write 1 over 6 to the power 2, x to the power 2, and y to the power 2. Simplifying it a little bit, it's going to give us 1 over 36, x to the power 2, and y to the power 2. Looking at question number 3, we got x to the power 2 and y to the power 3 divided by x over y. We can write it like x to the power 2 divided by x and y to the power 3 divided by y. Using a laws of exponents, we can write x to the power 2 minus 1 and y to the power 3 minus 1. We know that the power of x and y is 1. So we're going to get x to the power 2 minus 1 is 1. We don't need to write 1. And y to the power 3 minus 1, it would be y to the power 2. So that would be our answer. The process of taking powers can be inverted using logarithms. The logarithm of x with respect to base b is defined to be the number y such that b to the power y is equal to x. We're gonna call it logarithm of x with respect to base b. Or we can write, for example, log of 100 with respect to base 10. So we need to think, what is a number that we have to raise the power 10 to get 100? So what could be the power of 10 that gonna make 100? So in that case, we know that the power of 10 should be 2 to make the 100. In that case, the answer for log 100 base 10 would be 2. What are the values of log 4 base 4? We can call it log 4 base 4 is the number y such that 4 to the power y is equal to 4. So we know that the power for this 4 is 1, so y would be equal to 1. In second question, log 3 base 27 is the number y such that 27 to the power y is equal to 3. We can simplify it a little bit. We got 3 here, the power for 3 is 1, and we can convert 27 into 3 to the power 3. We got already y there is equal to 3 to the power 1. Now we can see we got 3 here, we got 3 here. We can write 3y is equal to 1 and y would be equal to 1 over 3. The logarithm of 3 with respect to base 27 is 1 over 3. Looking at question number 3, log 0.1 base 10 is the number y such that 10 to the power y is equal to 0.1, or we can write it 10 to the power y is equal to 1 over 10 or 10 to the power minus 1. So we got 10 here, we got 10 here. In that case, we can write y is equal to minus 1. So the logarithm of 0.1 with respect to base 10 is equal to minus 1. There are different number system with different bases. For example, when we are talking about decimal number system that is of base 10, decimal number system with a base 10, we have 10 numbers starting from 0, 1, 2, 3, 7, 8, and 9. In that number system, we know that every number has its weight according to its position. For example, if we have 4764, the weight for this 4 is, let's say, 1000. It's making 4000. Weight for 7 is 100 according to its position, and it's gonna make 700. Weight of 6 is, let's say, 10, and it's gonna make 60. And weight for 4 is a unit, so we're gonna write 10 to the power 0. And 10 to the power 0, we know that anything to the power 0 is 1, so it would be a 4. So in decimal number system, every number has its weight according to its position, and we have represented that 4 is a unit. It has the first number, we have represented that one by 10 to the power 0. 6 is in 10, so 10 to the power 1. 7 is 100, so 700, or 10 to the power, it could be written as a 10 to the power 2. The weight for 4 according to its position is 1000, or we can write that one 10 to the power 3. Similarly, we got other number systems. When we'll be talking about binary number system or base 2, in binary number system we got two digits 0 and 1. There's some common number system that we are using in computing. When we're looking at octal number system, in octal number system we got 0, 1, 2, 3, 4, 5, 6 and 7. There are 8 digits in there. And when we are talking about hexadecimal number system, hexa means 6, decimal means 10, so a number system that has 16 digits in there, starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for 10 we're using alphabets A, B, C, D, E and F. 10 is represented by A. For 11 we are using B's, C, 12. For 13 we are using D. For 14 we are using E, and similarly for 15 we are using F. We all know that how base 10 numbers work. For example, if we have 397, each number has its weight according to its position. For example, 7 is unit, so its weight would be 10 to the power 0. Similarly, 9 is in tens, so it would be 10 to the power 1, and 3 is 100. So it's according to its position, its weight would be 10 to the power 2. When we have to write a number in base 10, it means an minus 1, an minus 2, and so on till a3, a2, a1, a0. And then here we got a decimal point, and we have C1, C2, and CM is the, let's say, last term. When we're gonna write in using sigma notation, it would be sigma I starting from 0 till n, a I 10 to the power I, plus for decimal portion of the number it would be j is equal to 1 till m, that is the last term, cj, and 10 to the power minus j. Similarly, when we'll be talking about base b, it means we need b digits in base b number system. General formula for base b would be sigma I starting from 0 till n, a I and b to the power I. And for decimal part, it would be j starting from 1 till m, c, j, and b to the power minus j. We can see that in base 10 we have used 10 there, 10 there. and in base B we'll be using B instead of 10. We need to convert these numbers to base 10. We got 112 base 3. When we'll be converting them into base 10, it would be, we know that the 2 is the position for 2 is unit, so 3 to the power 0 plus for 1 it's in 10 place, 3 to the power 1 plus 1 multiplied by 3 to the power 2. 1 multiplied by 3 to the power 2. Once we're gonna simplify them, it would be 3 square would be 9. 3 to the power 1 is 3 multiplied by 3 is 3. 3 to the power 0 is 1 multiplied by 2 is 1. So it would be 14 in base 10. Next question, 18 base 16. So what we're gonna do, 8 multiplied by 16 to the power 0 because 8 is in unit position plus 1 is in 10 position, 16 to the power 1. Once we're gonna simplify them, 16 to the power 0 is 1, 8 multiplied by 1 is 8 plus 16, it will be 24, base 10. Normally with the decimal number system we are not writing base, so if we're gonna write 24, it's understood, it's in base 10. Question number 3 got two parts. One is 210 and the other one is decimal part. Let's try the both parts separately. We got 210 first. So what we're gonna do, we're gonna multiply 0 multiplied by a to the power 0 plus 1 multiplied by a to the power 1 plus 2 is in 100 position, it would be a to the power a to the power 2. And after simplification, 0, a to the power 0 is 1 multiplied by 0 is 0, a to the power 1 is 8 multiplied by 1 is 8 plus 64 times 2, so it would be 64 multiplied by 2, 100 and 64 multiplied by 2, it would be 128, I think. Once we're gonna simplify them, we're gonna get 136. And looking at the decimal part, we got 0.4. So we know that the decimal part, we are multiplying them with a to the power minus 1 plus 4 multiplied with a to the power minus 2. Once we're gonna simplify them, 0 multiplied by a to the power minus 1 would be 0 and plus 4 over a to the power 2, it would be 4 over 64 or 1 over 16. So over altogether our answer would be equal to 136 and 1 over 16. 136 side 1 over 16, that would be the conversion of 210 octal point 04 into decimal into base 10. To convert an integer from base 10 to another base, we use the following methods of division. Let's take any number. For example, we're going to take 108 with base 10, and we need to convert that one into, let's say, base 7. We're going to use the method of division. We will be dividing 108 by 7 in this way. How many 7s are there in 10? There is 1, and the difference is 3. And how many 7s are there in 38? 7, 5 times 35, and remainder would be 3. How many 7s are there in 15? 7, 2 times 14, and the difference between 14 and 15 is 1. Remainder would be 1. So when we'll be converting 108 from base 10 to base 7, it would be equal to, we need to start from here and then we're gonna go up. It will be 2, 1, 3. That is a conversion of a number with base 10 or decimal number to base 7. Remember, when we'll be looking at in the last slides, we have done that when we'll be looking at position and weight of each number, then in that case it will work like this. The position of 3 is unit and its weight would be 7 to the power 0. 1 would be 7 to the power 1, and the position of 2 is 100, so its weight would be 7 to the power 2. And once we're going to multiply them, 3 with 7 to the power 0, 1 with the 7 to the power 1, 7 to the power 2 with 2, we'll be getting 108. Conversion of decimal number systems to base 2. For example, we have 126 to the base 10, and we need to convert that one into a binary number system. We're going to use the same method of division. We got 126. We need to divide 126 by 2. 2 6 times 12, and 2 3 times 6. Remainder would be 0. Again, we're going to divide by 2. 2 3 times 6. 2 1 times 2, and remainder would be 1. Going to divide by 2. 2 15 times 30, remainder 1. 2 7 times 14, remainder 1. And 2 3 times 6, remainder 1. And 2 1 times 1, remainder 1. So when we have to write that one, we'll be starting from this one, and we're gonna go up like this. It would be 1 1 1 1 and 1, and then we got that 0. So conversion of 126 in decimal number system to a binary number system, that is base 2, it would be 1 1 1 1 1 0. Another example could be converting 54 from base 10 to base 5. If we have to convert any decimal number to any given base, we need to divide that number with that given base. For example, in this case, we're converting 54 from decimal to base 5, so we need to divide 54 by 5. 5 1 times 5, and 4 is smaller than 5. We're going to put 0, and remainder would be 4. 5 2 times 10, and the remainder would be 0. So when we'll be writing, we need to start from Z2 and then we need to go up. It would be 2 0 4. So conversion of 54 from base 10 to a base 5, it will be 2 0 4. And we have discussed the weight and position already. If just in case if we have to convert any base 5 number to base 10 or decimal number system, we can convert any decimal number to any base. For example, if we'll be having, let's say, 103 in decimal number system or base 10, we can convert that one into base 6. In that case, what we need to do, we need to divide 103 by 6. 6, 1 times 6, and difference between 6 and 10 is 4. So we're going to put 4 there. 6, 7 times 42, and remainder would be 1. Again, we're going to divide by 6. 6 2 times 12, and remainder would be 5. So we need to start from this 2. We're going to go up like this. It would be 251. The conversion of 103 from decimal number system to number system that has a base 6, it would be 251. And similarly, we know that the 1 has the position for 1 is unit. It will be 6 to the power 0, 6 to the power 1, and the weight for 2 would be 6 to the power 2. Let's look at one example where we'll be converting one decimal number into different number systems. Let's take one decimal number 60, and we need to convert that one into base 2, and then maybe into base 8, and then into base 16. The conversion of 60 to base 2, we need to divide 60 by 2. 230 times 60, remainder 0. 215 times 30, remainder 0. 7 times 14, remainder 1. 3 times 6, remainder 1. And 1 times 2, remainder 1. It would be 1 1 1 1 0 0. When we'll be converting 60 from base 10 to base 2, it will be 1 1 1 1 0 0. Now we need to convert 60 from base 10 to base 8. We'll divide 60 by 8. So 8 7 times 56, remainder would be 4. So we're going to start from this 7, and then we're going to go up. It would be equal to 74. 74. And when we have to convert 60 from base 10 to base 16, we need to divide 60 by 16. 16 3 times 48, and the remainder would be 12. So we know that in hexadecimal number system or base 16 number system, 10 is represented by A, 11 is represented by B, and 12 is represented by C. So this 12 gonna get replaced by C. So conversion of 60 from base 10 to base 16, it would be equal to 3C. And we know that if we have 13, like we got D, E, and F, that is 14 and 15. So that is a conversion of one number into 3 different number systems, base 2, base 8, and base 16. And you can just have a just a little bit of food for thoughts. You can see that in binary number system, it's going to take roughly 6 bits, and in octal it's taking 2, and similarly in base 16 hexadecimal, it's again taking 2 bits.